So hello and welcome. This is Carlos Acuna. I'm explaining my honors project for linear algebra. A little bit about me. I'm from El Salvador. I moved on 2015, and I spent a whole year learning English at the adult school. I needed to improve my speaking abilities. I wasn't able to communicate at first, and I really had a hard time just trying to, you know, speaking to other people and kind of relate. In this welcome page, I describe a little bit more about me. I include a couple pictures of me doing some hobbies, going to the beach, and then let me discuss about my goals in life. So my future plans is are to move to Southern California. I would like to transfer to either UCLA, UC Irvine, Carpoli Pomona, or San Luis Obispo. My major is mechanical engineering, and I'm looking forward to get a master's degree in robotics as well. I would like to create patents and sell my own inventions in like relatively close future. So that's kind of like my ending goal. Just create something, sell it to other people. Okay, so for my honors project, I had divided as the homepage, which includes the welcome and goals, the institutional learning outcomes, STEM learning outcomes, the major courses I have taken. The honors linear algebra include the introduction. These are the three topics I talk about. I'm gonna go in depth about it. This is the last honors project from differential equations. My community involvement and resume. Let me discuss about the abstract for linear algebra. So the goal is for this honors project to utilize concepts of linear algebra in several applications that includes balancing equation, solving network flow problems, the predator prey systems, and application to differential equations. The honors project includes concepts of the book, problems from chapter 1.6, 5.6, and 5.7. Okay, so let's dig in. So first of all, I discuss how to do balancing equations. We have been provided by a equation, a chemical equation. It has four elements, and each of them has an amount of elements on the left and on the right. And as you can see, for example, this one right here, there's two atoms of bottom, and one atom of bottom on the right. That means it's not balanced. And there's another indicator. There's two atoms of hydrogen here, and five atoms of hydrogen on the other side, adding them two together. So to balance this equation, we need to find a way to multiply each element by some amount and get the right numbers on the left and on the right. But linear algebra provides a better way to do it. This system is straightforward, it's faster than the other one. And honestly, I would have loved to know it before when I was taking this class. So let's set up the new equation with x's, x1 for the element 1, x2 for the element 2, x3 for the element 3, and x4 for the element 4. So each of them, we're going to create one vector in R4 that contains the amount of each element in the each of the atoms in the element. So for example, this one, the first one, if we arrange it as boron, sulfur, hydrogen, and oxygen, the first one will contain two atoms of boron and three of sulfur. And then the hydrogen and oxygen rows will be empty because there's no hydrogen and oxygen in that element. We do the same for the other ones. We fill it up. Then we proceed. We can say, okay, this equation, so the reactants equal to the outcome, right? Then we proceed to take all of them to one side so we can achieve AX equals 0. And then we can create an augmented matrix out of it. So actually A contains all of the elements. The first element, column 1, the second element, column 2, etc. To find x, so the values of the scalars that multiply each element, we need to set up the augmented equation. So this is the regular equation, matrix A, augmented with 0. We row reduce it, and what we get is these three depend on the free variable. So we have a free variable, and in this equation, usually what they look for is that it's you multiply. So they don't want decimals. First of all, they want whole numbers. So you need to multiply to a number that will make it as a simplified version of it. So we have to now have whole numbers, and it has to be simplified. So in this case, the one that will make us achieve that is x4 equal 3, because x3 and x1 is a fraction depending on 3, and 2 doesn't really matter. If we multiply by 3, we will achieve the simplified version of the balanced equation, and that will be the end answer. I can show you how to arrange it. So if we multiply by 3, x is equal to 1, x2 it will be equal to 6, x3 will be equal to 2, and x4 will be equal to 3. So the solution for this equation, now that it's balanced, is this one. 1 over here, 6 over here, 2 for the third element, and 3 for the fourth element. I provide a couple more examples of it. There's actually 3 examples I made. One of them has 5 variables, so it gets a little longer, but it's pretty much the same idea. So let's talk about network flow now. So network flow are used in planning for traffic. Engineers use it for that. In science, you can also apply the concepts for circuits and electricity. But in this case, I mean, it's pretty much the same, but it has some of the extra rules. So we're going to explain how it works, and then based on that, I can just show you that I got more examples of it. So for example, this one says find the general flow pattern on the network shown in the figure, assuming all that flows are all non-negative. What is the largest possible value for x3? So in this case, we got this figure right here, and we want to solve for x1, x2, x3, and x4. And we are provided with two actual values, 80 and 20. So based on that, we're going to solve it. Now, how can we proceed about this? So what it is that we're going to position on a node on one of the intersections, and we're going to say the flow in, so whatever is going in is equal to whatever is going out. In this case, A, for example, has x1 and x3 going in and 20 going out. X2, and for B, junction B, x2 is going in and x3 and x4 is going out. For C, 80 is going in and x1 and x2 is going out. So we proceed, we get now this system of equation. We can find the total flow by adding these three together. So we got x1 will cancel x1, x3 will cancel x3, x2 will cancel x2, and what we're left of is 80 equal x4 plus 20. That's the total flow. We can now solve, so we're gonna leave the scalars on one side and all the variables in the other side. So we can solve for the x values. So let's set up that augmented equation. This is the solution for it. This is an equation that we can solve easily. x1 here will be represented by 1. x2, there's no x2, so we need a 0. 1 for x3 and 0 for x4. If we row reduce it, we find out these values. And then what it is it says x1 is equal to 20 minus x3, x2 equal to 60 plus x3, x3 comes up to be a free variable, and x4 is actually 60, so we don't need to do nothing for it. That one is already solved. However, it says what has to be the value for x3, because that's constrained by x1, right? So if you see that, it says it cannot be negative. But if x3 is more than 20, we get a negative value. It doesn't matter if it's 0, but they do care about being negative. So in this case, because we cannot be more than 20. Let's give the value of x3 equal to 20. And we can now tell that x1 is 0, x2 is 80, x3 is 20, and x4 is 60. This is how the pattern look. It's already solved. 20, 80, there's no flow here. 20, 80, and 60. So that's how you solve it. It's very little information they give you. If we got a free variable, as you see, it's because we might need a little bit more extra information. But however, it doesn't mean we cannot solve it. You can always make up some values and say, oh, okay, if this was to be 20 in this case, then this will be the other values. So I explained two more problems. This one is more complicated, and the last one is a little bit more complicated than the other two. And it's just a larger system of equation is 1, 2, 3, 4, 5 system of 5 equations, and then we can solve for it. So that's good. So now we know how to apply it. And then let me talk about now on discrete dynamical system. So for discrete dynamical systems, first of all, we need to know how to classify the origin. To classify the origin, we have three denominations. So if lambda 1 is more than 1 and lambda 2 is less than 1, then the origin is a saddle point. So the direction of the greatest repulsion is to the origin and the eigenvector 1. The direction of the greatest attraction is to the origin and the eigenvector 2. Then the other case is if lambda 1 and lambda 2 are both less than 1, the origin is an attractor. So it's pulling them inside, it's pulling them to 0. And the direction of the greatest attraction is to the origin and the eigenvector 1. If lambda 1 and lambda 2 is more than 1, this means the origin is a repeller, and the direction of the greatest repulsion is to the origin and B1. So we gotta keep that in mind. I'm gonna tell more about it on the predator-prey system, how to apply it and what it means. But in this case, I'm just gonna show you one example of how to get those values and what's going on. So for example, this one, it says matrix A. They give you matrix A, and then it says classify as an attractor, repeller, or a saddle point. So this is the form of the dynamical discrete systems, x k plus 1 equal to a x sub k. Find the direction of the greatest attraction or repulsion. That's what they want. So to solve this, we first need to find the characteristic equation. So a minus lambda I, we can get the determinant. We get lambda squared minus 2.5 lambda plus 1 is equal to 0. Therefore, the quadratic equation will give us the solution for it, and it comes to be lambda 1 equal to 2 and lambda 2 equal to 0.5. So the origin is a saddle point because lambda 1 is more equal to 1, right? And lambda 2 is less than 1. So the direction of the repulsion is to the origin and the eigenvector 1. So to find the eigenvector, we now need to use the value for that lambda, which is lambda 1, and solve for the equation. So we augment this equation with 0. This is the original equation augmented with 0. Row reduce it. x1 is equal to negative x2, and x2 is a free variable. Therefore, b1 is negative 1 and 1. And now we can find the direction of the greatest attraction. So that's to the origin and the eigenvector. And we just substitute the lambda 2 here in this equation. And we augment it with 0. This is the equation for the matrix A minus lambda, and augmented with 0. We can now get the value x1 equal 0.25, x2, which is equal to 1/4, x2 equal 3. That means that the vector 2 is 1 and 4. So that's how it is. Now I'll show you what it means with an application, such as the predator-prey system. All right. So in this one, they give you a matrix. It says in all grove forests of Douglas fir, the spotted owl dines mainly on flying squirrels. So they only eat flying squirrels. Suppose that the predator-prey matrix of these two is this one. So now, show that if the predation parameter P is 0.325, both populations will grow. Estimate the long-term growth rate and eventual ratio of owls two flying squirrels. Now, the part B says, show that if the predation parameter P is 0.5, both the owls and the squirrels will eventually die. So let's solve part A. We need to set out the A minus lambda, as I said before, you get the characteristic equation. We find lambda 1 equal to 1.05, and lambda 2 equal to 0.55. So based on that, now it says, okay, one eigenvalue is larger than the other one. And this one right here is more than 1. This one right here is less than 1. Therefore, the relative sizes are determined by the entries of the eigenvector 1. So that's the eigenvector that defines the direction of the largest repulsion. So the largest repulsion will tell us the relative sizes in long term. Okay, so we got that set up. We got this matrix A, the new matrix A, and augmented with 0. And now this is the vector 1 that is the long-term relationship between the squirrels and the owls. So now let's interpret that. It says eventually there will be about 6 spotted owls for every 13,000 flying squirrels. All right, so we got that. That's the interpretation. That's because this is a repulsor, and it will give us the long-term behavior of it. Now let's solve for part B. If we substitute B to be equal to 0.5 in the original matrix, now get the eigenvalues for that. We got both to be less than 1, 0.9 and 0.7. So now we know both magnitudes are less than 1. So the origin is attracting them, this dynamical system. So the trajectories of these two will go toward to 0. So they will approach 0 in the long term. So this means that the population will eventually perish. So they will die. Okay, so that's how you prove it. That's the application of it. I give you 2 more examples here. Example number 2. Well, actually, this is the other example. So I give you 2 examples of this. This one is more complete. You can check it out. It talks about how to set up the action matrix when they give you the values, and then how to interpret it. This one is a little bit more in depth. So, moreover, let's talk about the differential equation with linear algebra. This one is very similar to the other one, to the discrete dynamical system. The only exception is that now we got the general solution for this differential equation, and we got the initial value. So this is more like an initial value problem where we deal with eigenvectors, eigenvalues, and we can set up the general equation. That's how it is. So now, for this example, it says a particular moving particle in a planar force field has a position vector of x that satisfies x prime equal to ax. The 2 by 2 matrix A has eigenvalues 4, 2, with corresponding eigenvectors, and they give you B1 and B2. So we got the eigendata, and now they say find the position of the particle at time t, assuming that this is the initial condition. So if we know xt equal to c1 b1 e lambda 1 t plus c2 b2 e lambda 2 t plus cn bn e lambda n t, so it could go over for as many eigenvalues we have. So we say, okay, good, we know that. So let me plug in b1 is my first eigenvector, lambda 1 is the first eigenvalue, b2 is the second eigenvector, and lambda 2 is the second eigenvalue. We know that, and now let's use the initial condition value to solve for C1. So we have C1, this is B1. Now we plug in t equals 0 for both of them. And we're going to make it equal to the initial conditions, right? So we got, this is x of 0. And now we got this new matrix because this is 1 and this is 1. We just got a C1 plus C2, C3 matrix that we can solve, we can find by setting up these two matrices together and augmented with the solution of it. So we got here, this is a matrix, usually P, that's how they call it, P, augmented with the solution of it for the initial condition. We now row reduce it, and we find that C1 is equal to 5 over 2, and C2 is equal to negative 3 over 2. So that's pretty straightforward. We got 5 over 2 times the vector 1, e to the 4t, minus 3 over 2 times vector 2, eigenvector 2, e to the 2t. So that's the solution of it. I'm going to show you one more example. In this website, I got 3 of them. So this is example 2, and this is example 3. But I got to show you this one, because this one contains a little bit more of you have to do a lot more work for it, and you actually interpret a little bit of it. So let's walk through it. So it says solve the initial value problem x prime of t equal to ax of t for all t's more than or equal to 0. They give you the initial conditions is 3, 2. That's the initial condition vector. And then classify the nature of the origin as an attractor, repellor, or the starting point. So in this case, we gotta find the eigenvectors and eigenvalues from the matrix they give us. Plus, we need to classify it and make the general solution for this differential equation. So let's start. We got the matrix A. We now need to find the characteristic equation. We now found that L1, lambda 1 is 1, and lambda 2 is negative 1. Therefore, let's look for the eigenvector 1. This is how you get it. B1 is negative 3 and 1. So this is the direction of the greatest repulsion. It's to the origin and eigenvector 1. So this is the greatest repulsion. Now let's find eigenvector 2. Same thing. We now set out the equation A plus 1 equal to 0. So we set up this augmented with 0, row reduce it. We get vector negative 1 and 1. This is the direction of the greatest attraction and the line to the origin. So line to the origin and eigenvector 2. That's what it is. That's why we get it. So now let's consider the initial condition they gave us. All right. So we got x initial at 0 equal to 3 and 2. We know the general solution. Therefore, we set up eigenvector 1. This is value of lambda 1, value of lambda 2, eigenvector 2, solution for it, and we set up all the t's to be equal to 0. We therefore get just these two eigenvectors and the final solution, and we want to find the c's. We find the c's by augmenting the matrix P with the solution for the initial condition. Now we find that C1 is negative 5 over 2 and C2 is equal to 9 over 2. Therefore, the solution for this differential equation is equal to negative 5 over 2 eigenvector 1 e to the t because lambda 1 is 1 plus 9 over 2 eigenvector 2 e to the negative t because lambda 2 is equal to negative 1. So since the one eigenvector is positive and the other is negative, we say the origin is the starting point of the dynamical system described by x prime equal to ax and the origin. So this is how you do it. That's the application of it. We apply eigenvectors, eigenvalues, and we apply the solution. We already classify it as well as a starting point, and we find the solution for the general equation. So three things in one. It's very helpful. It can actually speed up things. And there's one more thing I want to talk about is how to decoupling a dynamical system. This one is important. I give one example on this because sometimes it might be too complicated to solve one of the equations through the variable x. So we can find a way to move around things and get it to the value y, get the solution, and then go back and plug it into x again. So for this thing, we got information as x prime equal ax. That's information we have. We also know that xt equal to pyt. That's the thing we need to know. And they also say we need to prove that this leads to y prime equal to dy. So let's go for it. Matrix A is 7, 3, -1, and 3. We are given the eigenvalues and eigenvectors. So to establish this equation is more of a, move things around and see how it goes. So x prime equal ax, we must set the matrix P that contains the eigenvectors. So P is equal to eigenvector 1, eigenvector 2, and let's let D be equal to the diagonal matrix containing the eigenvalues. So based on the diagonalization of the matrix, we know A is equal to P D P inverse, and D is equal to P inverse AP. If we substitute xt equal to pyt into x prime equal to ax, so we know x is equal to pyt, so let's change it. We got d dt, because that's the prime, that's the derivative of py, which is x, equal to a times x, which is py. So now let's do this. A, we know is p dp inverse, so we can cancel p, and we are left with p dy. So d dt py equal to p dy. Now, the matrix P contains only constant entries. Therefore, if we take derivative of it, because it's multiplying the variable, it won't change. So we can left P outside, take derivative of y, and make it equal to P dy, because that was what it was equal before, right? We just move the P outside, we leave this one inside. So now we can get rid of P by multiplying to P inverse on the left side to both sides, obtaining a change in variable. So now we are left with d dt, which is equal to y prime, and that's equal to t dy. Or we can express it as, the entry 1 of y1 prime and the entry 2 of y2 prime equal to the diagonal matrix containing the eigenvalues times y1t and the entry 2 y2t. So decoupling or detangling, right, is useful when we have a complicated set of linear equations. That might be easier to solve by changing the variable. If we change the variable from x to y, this equation can be just easier. And then there's one property that is very important. Every y prime is equal to lambda prime y1. So the solution only depends on itself. And we find the solution of the differential equation to be yt c1 e lambda 1t plus all of the other values for each individual lambda. So in this case, what it means is that we could find the solution for this, and then because we find the respective initial condition, they give us the initial condition, we can find the values for c in this equation, for the yt, which is the decouple equation, which later we can just say, okay, we know that xt is pyt, right? We now know the values for yt. And then p is just the eigenvectors, right? It's the matrix containing the eigenvectors. So we just multiply this eigenvector times yt, which contains c1, e lambda 1, and t for each individual lambda values. And that's how we do it. That's what it is. It's very useful. I think that if you have a complicated linear set of equations, or differential equations, this will actually get you out of any trouble you have. Okay, well, most of the troubles, honestly. Thank you and have a nice summer.